Okay, so let's move on to multiple bonds. If you run out of electrons to satisfy the octet rule, then you are allowed to make a double or triple bond. So I'm going to write that down. And you would create these bonds by sharing electrons. And I'll show you how to do that. Okay. So in an earlier section, I believe we talked about the differences between single and triple bonds in terms of bond lengths and their strengths. So you can see here that we've got the bond energy in the second column and the bond length in the third column. So here they're showing you that the single bonded carbon is the longest, and then the triple bonded carbon is the shortest, and that we have the most energy, or the strongest, when we're talking about triple bonds, and then single bonds would be the weakest. Okay, so let's move on and let's go to the next page, and I'm going to show you how to create a double or triple bond when needed. Okay. Okay. We're going to start with carbon dioxide. So for carbon dioxide, we want to make it look symmetrical. So you put the carbon in the middle with the oxygen on either side, connect them with single bonds. Carbon's in 4A, oxygen's in 6A. So 4 plus 2 times 6 would give me 16 valence electrons. Now, I used how many electrons when I drew in my single bonds? 4. So 16 minus 4 is 12. So I'm going to put the remaining 12 wherever I want. 2, 4, 6, 8, 10, 12. Do you see how I ran out of electrons before I could put 8 on the oxygens? Okay. So in this case, we have to move a pair in here so that we can share it to satisfy the octet rule. So when I do that, I get something that looks like this. Okay, so now this oxygen that's on the right-hand side, this would be surrounded by, actually I shouldn't have drawn it that way. I'm gonna get rid of that. Yep. This oxygen is now surrounded by 2, 4, 6, 8. So this oxygen's happy, okay? This oxygen over here is only surrounded by 6. So it's not happy. So that means I need to move another pair. So I'm going to take this pair on carbon and I'm going to put it here. And when I do that, I end up with something that looks like this. Now each oxygen is surrounded by 8, and so is the carbon. So everybody's happy. So now I'm done. Okay? And remember how before I said in a previous section, carbon loves to have 4 bonds. Okay? It does. Oxygen loves to have 2 because oxygen has 6 valence electrons, so it needs 2 more. Notice the oxygen has 2 on each one. Okay, so it makes it happy. All right, now let's take a look at the next page. Okay, on the next page, they talk about expanded octets. So I'm going to highlight the xenon here, because xenon is in the 5th period. So that means xenon has d orbitals. It has the ability to accommodate more than an octet. If we're looking at XeF4, xenon is in 8A, fluorine is in 7A. So it's 8 plus 4 times 7, so this is 28 plus 8, this is going to be 36. I have 36 electrons to work with, okay? So we've got 2, 4, 6, 8 when we drew in our single bond, so that means you've got what, 28 left? 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. So 24 are on the fluorines. That means we have to put the extras on the central atom, and we can do that because xenon is in the 5th period and it can accommodate them. This doesn't happen very often. It happens like 5% of the time. Okay, like even less than that. You won't see these very often. Okay? Okay, let's turn to the next page. Okay, I want you to take a look at the practice problems with the person sitting next to you. I want you to draw 1, 2, and 3, and let's see what you guys come up with. Okay, formaldehyde looks like that. Is that what you guys got? Okay, hydrogen is an exception. What you might want to do as you go through these is you may want to highlight the element that is an exception in the chemical formula on the lab so that way you don't make that mistake, okay? And then for carbon monoxide, so you've got it connected here. So it's 4A plus 6A, so that means you've got 10 electrons. Subtract 2 when you drew that single bond. 2, 4, 6, 8. So that means you have to move a pair here. Okay, carbon's still miserable because carbon's only surrounded by 6. So take another pair, put it here. That's how you get something that looks like this. There's no way for you to make more than a triple bond. Okay, I realize I said earlier that carbon prefers to have 4 bonds on it, but there's no way to make that happen in this situation. Okay, for number 3, bromine's in the middle, surrounded by 3 fluorines. This is 7 plus 3 times 7. What's that? 28 electrons total. We drew in 6 with our single bonds. You've got 22 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Done. Any questions on that? Last page. Okay, we're going to talk about drawing ions and then resonance, and then we are done. Okay. All right, at the top we've got the ammonium ion. So ammonium is NH4 plus 1. So you've got 5A and 1A. So 5 for nitrogen, 4 hydrogen and 1A, subtract 1 valence electron from the total because of this plus 1 charge, which tells you that you lost 1 electron. So that means we have 8 electrons total to work with. You draw it as you would normally draw it, but ions require brackets in their Lewis structure, so you had to add this part, and then you have to put the charge on the outside. Okay? And then lastly, let's talk about resonance. Sometimes you're going to be able to put a double bond in more than one location that looks identical to another one. This often happens with oxygen. So here our example is the carbonate ion. The Lewis structure for carbonate looks something like this. Notice that we've got 3 oxygens. Couldn't you have put this double bond on any one of those oxygens? And it's kind of equivalent, okay? So when you have something like that, you have to show all 3. You have to put double arrows in between the structures. And regardless of whether it's an ion or not, you have to put brackets around the chemical structure that you drew. Okay, so let me make a note here that brackets are required in resonance structures. And technically, so is the double arrow. Okay. Now, you might think that if we were to take a picture of this molecule, like in real time, that we would see this double bond in one of those 3 locations. But in reality, that's not what's happening. These electrons that are involved in the double bond are actually spread out between all 3 of these bonds. So we say that they are delocalized. So delocalized electrons are what you have in resonance. That means they're not associated with any one pair of bonded atoms, but they spread themselves out equally between all 3 pairs. Since we can't really show that, it's just assumed that you know that, okay? And what that means is this single bond is actually shorter than you would anticipate it to be, and this double bond is actually longer. So here it says slightly shorter than a single bond, slightly longer than a double bond. So that means it's somewhere in between. And then I think that might be all that I need to say. Yeah, that's pretty much it. And then the questions that you guys had about the lab, I think there was like an HONO structure, and you asked me why is there an underline under the N? That's because the one that is underlined is the one that we would deem the central atom, and we would want to predict the shape and the bond angle around that, which you don't know anything about yet, which you'll learn in the next section. Okay, so sometimes you'll have a structure and you're like, I don't know if the carbon or the oxygen is my central atom. And so then I would have to tell you which one I would want to be the central atom so that you could predict other things around it. Okay? Okay, so on that lab,